So we're going to do something a little bit different today. I'm on the PC, yes, but I'm going to do something Amiga related. We are going to get the Amiga to play a sound, and we're going to do it with this Visual Studio Code plugin. This is Visual Studio Code here. This is a program from Microsoft. This is like a free, basically, text editor, but it does all kinds of things and it supports extensions. Now, one of the extensions in here, if you type Amiga-Debug in, there it is. Amiga C++ compile, debug, and profile. We're going to use this to create an Amiga program, and we are going to use the example program, and we're going to just actually strip out some of the stuff from there, and we're going to actually try and get the Amiga to play a sound. We're going to see how it's possible to play an Amiga sound by just directly manipulating the hardware, which is how you do it if you're making a video game or something like that, and you've bypassed the OS. So first thing I'm going to do is install this plugin, which has got a bit of a long title, but I'm going to install that. And that's pretty much it to start with. So let me just maximize this. So the page about this has actually got a quick start. It's actually really good, this, because it's got all this like kind of video. You can actually like look at what everything's doing and what the blitter's doing and all that kind of stuff. It's really quite cool. But it's got like a quick start there. Basically what it says is we need to create a new folder. We need to open a folder basically. So we do File, Open Folder. And I'm going to make a new folder here called Amiga Audio 1. You can see there's one there that I've already used before as I've been trying this out. So I'm going to select that folder. And yes, I trust the authors because the author is me. Now, we've lost the page where it was, but what you have to do is Control-Shift-P, and we want to do init Amiga init project. So this is going to create us a new Amiga project, which should actually provide us. So this is just like a really like short demo program that shows off like basically this whole project of how it compiles and builds. It's like only a 500 line program there. But basically, if I hit F5 now, it should build this and actually run it, and we'll get to see it. And it's actually got a little like program. It's got like, well, you'll see now. There you go. So that's what you get out of the box. It's actually got a mod player built in there. It's loaded in a picture, and it's done some blitting, and it's got a debug drawer and everything like that. So let me just make this bigger for you. Make this a bit bigger so you can read it a bit better. So first thing I'm going to do is I'm going to go into this program, and it's got a lot of stuff here. It's set up a copy list. It's set up an image. It's doing some scrolling. There's the copy list there. There's some assembly in there just to do the mod player. But what I'm going to do, the very first thing, is I'm going to just take out some of the code. I'm going to go down here. And we're going to rip out. Here we go. Here's some stuff. Like, so it's drawing some debug stuff. We don't want that. I'm just going to strip it down a bit because I don't actually want all this. There's a test blit here. I'm not interested in blitting because we are going to do audio for this particular demo, and there's a bit of screen clearing there going on. Let's get rid of that as well. So let's just get rid of all the stuff, and it also has a define at the top for music, and if we just undef that, we can get rid of the music as well. We don't want that because we're going to be playing a sound. So let's just run that and let's see what we get. Apparently nothing. That did not boot. Let's try that again. Don't know why it didn't boot last time. Yeah, there it is. So we just left with the main image, and it just scrolls left and right. That's fine. I'll leave that there as it is for now, just so we can see that something actually works. But the main goal here is to just get it to play some audio. One thing well, there's a lot of setup that's already been done in this program, but one thing it's worth being aware of is that it has set up this pointer to something that's called custom. Now, what custom is just this data structure that is actually all the, like, basically is a map of the custom hardware, or the registers for the chips in the Amiga. So everything's in there. So when the program starts, at some point it's going to initialize this. Where is it? Let's find it. There it is. So it's just initialized it to the base address of the of the custom Amiga hardware chips, and it's just cast it to this data structure that we've got. So basically, this custom thing, wherever you see this is going to be accessing all the registers in the custom chips. Like normally in assembly language, you'd be loading a register and doing an offset and then moving a value. But here we can just access this custom pointer directly because we're doing this in C basically. So that's the first thing to be aware of. Next thing is if we go down here, so what's actually happening here is there's a bit of a setup where it's setting up the screen and the copper and everything like that, setting up interrupts, and then eventually it gets to here, it just waits for a left mouse click, waits for line 10, and then increments the frame counter, and then we're going to do nothing, and that loops forever. So this program basically doesn't do anything. After it's been set up, everything else is being done by the custom hardware in the Amiga basically. But the main program itself isn't doing much. But what we're going to do is just here, just before it goes into its main loop, so that's the main loop of the program there, where it's waiting for the left mouse button. Here's where we're going to do we're going to play our sound. So we're going to do that here. So the first thing we need to do to play a sound is we've got 4 sound channels in the Amiga, and they are mapped into these custom registers. So it's basically got an array, and there's 4 of these audio, it's just AUD here. So inside there's like each one of these data structures is repeated. Let me just go to the let me go look at the custom hardware there. I think it's audio. Here we go. So inside here, we've got a map of actually 4 structures that are just to do with the audio. So each audio channel gets its own version of this. So this is what we're going to need to set up to actually trigger the Amiga to actually play something basically. So this audio 0, that's like the the first audio channel you can think of it. And one thing it's got is AC PTR. So what that is this is a pointer. This is a pointer to the data that we want to play. So we're going to make a sine wave, and we're just going to call that sine data for now. We haven't actually got that data yet, but we're going to put in some data that we're going to tell it that we want you to play the data that we're looking at. And we'll look at how that's formatted in a minute. Next thing is we need to know how many bytes we've got to play here. So let me just document for this. This is pointer to the audio location, and this should be in chip memory because the Amiga chipset is going to play this for us, and for the Amiga chipset to access anything, it has to be in chip memory, hence the name. So we've got to have a pointer to something that's in chip memory that we can actually give to this. Next thing here is the length of the data to play. And this length is actually in words, not bytes. So basically, we need to tell it how much we're going to play there. I'll leave that blank for now because we don't actually know yet. Next thing we need to know is the volume. So the Amiga volume for each channel. So volume is 0 to 64. So where 64 is max volume. So we just need to set the volume for the channel. We're just going to set it to max for now. So we're just going to max the volume of the channel out. Another thing we need to know is this data that we're going to play, how fast do we need to play it? So this is called the period basically, and that's just PER in this data structure. So that's another thing we're going to need to set. So this is the period. And we need to know what's that going to be. Then finally, so once we've set up all our data for that, we would actually have to tell the DMA, or the Amiga's chipset DMA, to actually just start. So we do that by actually setting the DMA control register. So this is DMA con, and to do that, there are some actual structures set up already in here to help us with this. The first one is this. So that is just going to, it's not actually finding it, but there is a reference to this. This is actually going to set the bit. I think this sets bit 15. Let me just find out where this is being defined. DMA bits, that's the one we want. Yeah, DMA bits. So this is actually just basically, there's a set clear bit here, and that tells us, if we set that, that tells us we want to set a bit, and then we need to set the bit that we're interested in. In this case, it's audio channel 0. So all this is really saying is start the DMA for audio channel 0. So that's just going to trigger the actual, like, the chipset to start playing the data that I've told it about. And also I've got to, well, I need to fill in the rest of this data here before we can make this work. But you get the idea here, is that we're actually trying to tell it what to do. So first thing I'm going to need is, see, because this won't compile yet, it's Control-Shift-B to just build. So let's actually define the data that we need for our little sine wave. And what I'm going to do is, there's already some like data in here that's part of this demo. There's these like bits of data for this you know, just doing like sine functions. But what I'm going to do is do something very similar to that, and it's a bit of a weird setup, but I'm just going to define some data right here, and this is how I'm going to do it. And basically there's a whole bunch of stuff here that is just telling this compiler that this stuff needs to go into chip memory. So it's going to be part of the, you know, it's going to be part of this program itself. It's being defined in the data, but I need some data here, and I'm saying put this in chip memory. It's going to be called sine data there, and it's going to be a bunch of bytes basically. So I'm just going to copy this in, but all this is just one cycle of a sine wave, and it goes between plus 127 and minus 127. So that's what the Amiga is expecting in its data, is a signed byte. So we're going from 0 there, we're going up to 127, we're going down, and we go back to 0, and then we go negative, and then we go back up, and then we can loop round and go back to 0. So this is just basically a little, really small amount of data that is just basically defining a sine wave. And this insane syntax here is just telling it to put it in chip memory when it defines it. So if we look at that, there is actually 1, 2, 3, 4, 5, 6. There's actually 12 bytes in this. So we go back, we now know the length. We know we've got the data, and we know the length of it that we need. So let's go back here. So the sine data has been defined. The length is actually 12, but remember that we specify this in words, not in bytes, and a word is 2 bytes, so we have to divide that by 2. So the actual length that we're gonna say, here's our data, and it is basically 6 words long. We're maximizing the volume of the channel, and we also need this period. So this is the bit where it gets a bit crazy, because what we have to do for this, the Amiga doesn't just specify like, well, it doesn't really just specify a sample rate or anything like that. But what we do have is basically the Amiga has this like clock rate, and it's the clock rate of the chips basically. So it's the number of ticks per second. So it's this number basically. It's different for PAL and for NTSC, but for PAL, I believe it's this number. And then we need to divide that by the, in this case, it's kind of like the frequency of the sound that we want to generate. So if we wanted to generate a 1 kilohertz tone, 1 kilohertz is 1,000 hertz, but we've also got, it's also got 12 bytes in the sample. So we need to times that by 12 as well. So this is all a bit strange, but what we're trying to do here is we're trying to give it the correct period to like, basically what we want to do is we want to play, we've given it a 1 cycle sine wave, but we want to actually tell it, we need you to play that at like as if it was 1,000 hertz. So that's what this period thing's going to do. So if I've got the maths right there, then this should in effect give us a 1 kilohertz sine wave. These are the kind of magic numbers that we've got here, and this is basically because this is just basically the number of ticks per second of the PAL machine. And yeah, you just have to look that up in the reference manual. But let's just run that and let's see if we get a sound, because it should, like, that's the setup, and then here's where we trigger the DMA basically. By the way, for DMA to work though, you do need to make sure that DMA is actually just completely turned on, and that has been turned on in this line here by this DMAF master. So DMA in itself can be globally turned off, but here at least DMA has been turned on, and then we trigger it by writing to the DMA control to say trigger channel 0, and I've just set up channel 0 to play there. So let's see if I got this right. Could have got it wrong. And I think that might be right. It could be right. I can hear the sound. Let's just see if we change that to like 2000 hertz. That should double the frequency of it. This might be wrong. Let's run it again and see if I've got this right. Yeah, so it seems like it's doubling. It seems like I've got it right, basically. So it all comes down to this like magic number here. The magic number, this is the magic number for PAL. And it's basically saying whatever the period is for that, is that's how fast we need to play it. So I've actually worked it out that, I want to play this at 2000 hertz or 1000 hertz or whatever. But it's doing it with just a 12 byte sample. And what's actually happening is when the DMA gets to the end of this, so when this 12 bytes reaches the end, the DMA just goes back to the start. And that's why this actually works, because we've given it one cycle, a one up and down cycle of like a pressure wave of sound. And then every time it finishes that, it just goes back to the start and continues. So basically, this is how the Amiga works. It will always just play a sound forever. You give it some bytes, and the DMA can play it, and it will just play forever, basically. So that's what we've done there. And we've constructed it ourselves just here by giving it a little bit of a sine wave there. That is actually pretty cool, because the cool part about the Amiga in this case really was that the chips are doing all the hard work. Here's all the CPU setup I had to do to play that sound. And then after that, I can just merrily go on my way with the processor. And the sound is just being played for me. So that's one of the reasons why the Amiga was so good at sound, is that, you didn't have to, well, you as the processor didn't have to do anything. It was doing it all for you. So there we go. So I think I've got that right. So that sound that you can hear is coming from the emulator. That's all pretty cool, but what about, and this is where it gets a bit more complicated, what about if I want to play back an actual sample? Let's say I want a sampled sound and I want to play that back. Now it's going to be very similar. So let's get rid of this. Let's get rid of this to start with. Let's get rid of that. And let's say we've got some sample data. We need to know the length of that sample data. And we want the volume again. And the period in this case, if we've got some sample data, is just basically going to be the number of samples per second. It's basically the number of ticks per second for the Amiga divided by the actual frequency of the sample. So if I'm going to do something at 1125 sample rate, then that should, in theory, play this back at the actual rate that it was sampled. So it's going to try not play it back higher or low. It's just going to play back the sample as it was. And again, to start it, we just need to trigger the audio there. So what we really need now is to get some sample data, and we need to know the length of that sample data, and we should be able to trigger it. The cool thing about the way this extension sets all this up, it does have a few little things. One of them is this. It's got this macro here that's actually, what it's doing is it's just taking a file and it's actually just including it directly into the executable. So you can see that image BPL thing there is actually the thing that's being shown on the screen when we launch it. It's the picture of, it says Abyss. So what we really need to do here, we can do the same thing here. We're going to include, I was going to call it sample data. Let's say sample.raw. We are actually just going to include our sample, and we need to say that it's chip memory again, because our sample has to be in chip memory. So we're going to make a file, and we're going to get it to be included directly into the executable, and then we can just actually play it. And the reason I'm doing that is then because I don't have to go through any like insane loading procedure, because this is only going to be a quick demo basically. But if I can get that data somewhere in memory, in chip memory, then I can play it back. All I need to know really is how much data have we got. Now, it's also worth noting that this audio length thing here is, yeah, this is a word. So it can only be 65,535 is the maximum number you can store in there, but it does specify words. So that really puts a limit on the maximum sample you could actually play on the Amiga before you'd have to stop and then continue on with the separate sample. But just to be aware of that, that's something you can work around, but just to be aware, you can't play like an insanely, 10-hour sample. You've got a limit on what you can actually play in here. So what I'm going to do, let's actually open Audacity, and I'm going to open a file. This is a huge file. It's stored as 32-bit audio, and it's stereo, all this kind of stuff. So the Amiga's not going to be able to play. It's also 48,000 hertz, which I don't think the Amiga can even do that. The Amiga wants 8-bit samples, and I think its maximum it can do is 28 kilohertz or something like that. So we need to downsample this, but a 28 kilohertz sample is going to be like use up a lot of memory in an Amiga. So we can't do that, but I'll just find a bit of this sample here, and we're going to cut it out. I won't play it to you now. I'll play it to you if we get it working in the actual demo. Okay, so I've converted to mono. Well, I actually didn't really convert to mono. I just rejected one of the tracks. And now I am going to export this, and I'm actually going to set to other uncompressed files, and I'm going to go raw headerless, and it's going to be signed 8-bit PCM. And basically PCM is pulse code modulation, and what that actually means is it's just the 8-bit bytes, and they're just in a stream basically. So that's all it really is. And that happens to be the exact format that the Amiga plays, because the Amiga is basically can only play 8-bit samples. So it's an 8-bit sample, it's PCM encoded, and it's got no header on it. Let me just save that in the correct place. Let's get rid of this. Go back to our program. Oh, it's just called sample.raw. So I'm going to change the name of it to sample.raw. And it's quite a long sample, but just looking at it here, it's 88,674 bytes. So I'm going to copy that, and I'm going to go down, and now it needs to know the length. So it's 88,674 bytes, but remember, it's specified in words, not in bytes. So I'm going to divide that by 2. So in theory now, if everything's worked here, when this compiles, it will actually include the sample that I've just made. It will set the length, it will set the volume, and it will say play it back at the rate that it was actually sampled at. So I turned it to 11025 sample rate basically, and it's basically this period gets set to that exact rate, and then it goes trigger the DMA and start playing it, and it should play forever. Let's see if this actually works. So there we go. So I took the Only Amiga song, and it's just a short section of it, and it's looping it. So yeah, that's an 88 kilobyte sample. So that's like, if you actually did that in an actual video game or something, you'd have taken like, most of your, if you did that on an A500, you've taken most of your memory doing that. So you probably wouldn't ever do this, but it just goes to show that this kind of thing is possible. Now, it's also worth noting that the sample just keeps playing. So when it gets to the end of this, like all the data for the sample, it just starts again. So we get this constantly looping thing. So if you wanted to trigger sound effects and stuff, that's not very good. That's not what you want. You really want to play the sound, and you want it to stop at the end. But remember, the Amiga just goes, oh, here's a bunch of memory, I'm going to play it, and then it just keeps looping and looping and looping. So if we want to take this one step further, what we're going to need to do is actually get an interrupt when the sample is finished, and then we're actually going to stop the sample. We've actually already got, as part of this demo, there's an interrupt handler here. So you can see here, what it's doing is it's setting up, basically this is a function. Let's just find it. There's a function here. Here's their interrupt handler. So their interrupt handler is basically just a function. And in this particular demo, it's happening during the vertical blank, which is, when the raster line gets to the bottom. And you can see here, this is what's doing that scrolling of making it move left and right. It's also playing the music if the music's enabled, and then it updates a frame counter. So we need another interrupt handler that tells us when audio is finished so that we can stop the audio. Well, we could actually write code into this interrupt handler, but one of the things about the Amiga is it has like 7 levels or 6 or 7 levels of interrupt. This one, even though it says interrupt handler, is actually only handling the interrupts at level 3. Now, level 3 includes the vertical blank, but audio is handled at level 4. So this interrupt handler won't actually work for audio. So we've got to set up another one. And you can see there, this is this int enable. This is basically turning on the vertical blank interrupt, and then it's going to be handled by this function. To stop our audio, we're going to need our own interrupt handler for level 4, which is the audio. We'll call this level 4. And we want to set in here, I think there is an audio, I think it's called audio 0. So there is basically there's an interrupt handler for each of the 4 audio channels. So I'm only using audio channel 0 here. So I'm only enabling that for that one. But basically what I'm going to have to do is, let's have a look at the interrupt handler code. This is where this is a bit weird, because this interrupt handler here, it's basically, this VBR is the vector base register. This is where the 68,000 basically stores all the pointers to its handlers, and it's got these 7. So this one's actually, it doesn't really say it here, but that's the one for level 3. So what we can actually do is we can do one for level 4. And I think that's going to be that one plus another 4 there, I think. So yeah, so this is a bit of like weird code, but it doesn't really tell you here. But basically there are many levels of interrupt, and this offset here is going to be the offset to the one we're trying to set. So this is how we're going to set interrupt handler level 4, and we basically also need a function to do that. So we're going to make a function just like the other one. Now there is something weird about this function, because it's got this attribute interrupt, and I think this has got some kind of special setup on it in this particular program, but I'm not sure. So I'm going to call this level 4. We're going to get rid of this stuff that modifies the scrolling copy list and the demo and the frame counter. And what we're going to do is kind of like what they've done, is we're going to clear the audio interrupt. Now it's actually saying it's doing it twice there because of an A4000 bug. I don't know anything about that, but we'll just stick with that. And then what we can do, we're going to clear the interrupt, but what we're actually going to do is we're just going to turn the DMA off for that channel. So it's DMA control, and to do that we just set the bit for the thing we want to turn off. So in this case, well, they're actually doing this thing where they're shifting this bit left, but we don't actually have to do that because it's actually got, they've actually got one to do that for us. So there's the bit for audio channel 0. So let's go and find that again. Yeah, they've actually got something that lets us do that. So we can actually swap this out here. So that is just basically this here, when you actually just write that bit into the DMA control, that actually turns the DMA off. So that's going to turn the DMA off for audio channel 0. So let's just see if this compiles. Let's run this and let's just see what we get. Now I'm going to show you the trick with this because this is a bit weird. Whoa. Well, that one, I wasn't expecting that. What have I done there? What have I done? Let's just see what we did. Oh. Okay, yeah, that's what I did wrong. I'm actually setting the DMA control to the interrupt, but actually this is I need the DMA. There we go. So that's what I wanted for the DMA control. I've actually set the wrong bit. So that sent that a bit crazy. Okay, let's try that again. So in theory, the interrupt gets handled and the audio stops. And I'm just getting a real high-pitched noise, which I don't know, I think I should be getting, but it's not playing the sound. So this is the trick with this kind of thing. What's actually happening is that interrupt's going to get triggered. It gets triggered when the sample first plays, but it also gets triggered when it restarts. So as soon as the sample plays, it triggers the interrupt handler, and then it actually just stops the sound. So let's just handle that. One of the other things we've got to do actually as well is, because this handles all 4 audio channels, technically what you should actually be doing is you should read the interrupt request register. You can actually test to see if this is audio channel 0. So that's what I'm going to do there. So first thing I'm going to test is this actually, something's happened on audio channel 0. So this interrupt request, this R thing on the end means this is a separate register for reading what interrupt has actually happened. And then we're checking to see if it's audio channel 0. And then if it is, we're going to stop the audio. So let's just check that still works. Or at least it doesn't work because it won't play the sound, remember. So that's the same as it was before. So what we've got to do now is basically we need to know when this has been restarted. So what I should really do is I could keep track of when I'm playing something, and every time this is called, I could increment a counter, and I'd know how many times it's been reset. So I don't want to reset it on the first count, but I do want to reset it on the second. And what I'm going to do is I'm going to this is basically just a 4-byte array that I'm going to define in the program, and I'm just going to do one for each channel. I'm going to just keep count of how many times the interrupt got called. So then what we can do is we can go in to the interrupt handler, where it is here. And what we can say is we know this is channel 0. So we'll say, okay, when channel 0 got called, then we'll increment this thing. So if we set it to 0 when it's first played, it will get set to 1 immediately, and then when it gets set to 2, we know we're looping around. So if this thing is actually equal to 2, then only then do we actually stop the audio. We actually handle that outside there actually. So only then do we actually stop the audio. So we could actually say that the sample is restarting when that equals 2. So yeah, so the audio interrupt is going to get called as soon as we play the sound, but then we only want to actually stop the sound when it comes through the next time. So every time we play a sound on a certain channel, all we've got to do is set the correct audio channel count to 0. So if we go down and find where we're playing, technically what we'd have to do here is, because we're starting audio channel 0, we'd set the play count to 0. So let's just see, in theory, that just plays our sample once and then stops the DMA. Oh, so it did stop, and then we got some getting some high-pitched audio. I don't know where that's coming from. That might be coming from maybe coming from this audio channel or something. But the DMA should be turned off for that one. Maybe the DMA for the other ones isn't off. But I don't know where that's coming from. But it's definitely done it. It's definitely worked. It's stopped the sample after one play. In theory, we can get it so it could play. This basically, if you set that to 3, it's going to play it twice. So it's going to set it to 1 minus whatever we said in there. So in theory, this would just play the sample twice. And then we get our high-pitched noise. Okay, so that is it really. I mean, I hope that wasn't I hope I explained that in some kind of decent way, but this just goes to show how cool the Amiga hardware was, especially when it came to playing sound, is that it's really not a big setup here. Like the audio interrupt handler stuff only has to be done once. This is the code that you need. This would be translated to machine code or whatever, but this is the code you need to actually launch a sample. And this is playing for like 4 or 5 seconds, isn't it? So that's all the CPU power you needed to get audio playing out one of the channels. And each one of these channels can play a different sample rate on each thing. But that just gives you an idea of what you actually had to do to get that to work. And also kind of how you can generate tones and that kind of thing and do looping stuff. With even only just a few bytes of data, you could get something working. So yeah, I hope that makes some kind of sense. And if you want to try this stuff out for yourself, you can download this Visual Studio extension and just mess about with this C program here that's got quite a lot of good stuff set up in it. Just to get you started on programming. A bare metal. This is bare metal programming, by the way. This isn't a call to the OS. The OS has been completely shut down here, and we are actually just bashing the hardware to get the to get it to do stuff for us. But that's why the Amiga was so powerful in the hardware department, because I have done virtually no CPU work there to get a lot of stuff coming out of the audio channel, and I can merrily carry on with the rest of my game doing whatever else I want, and that won't affect anything else, that audio. And I can do that 3 more times because there's 4 audio channels. So that's really cool. I know this is a bit of a different thing for my channel, but I hope I've made some kind of sense explaining that, and I hope that's interesting to some people out there who maybe want to work out how the Amiga works. There'll be people out here who know how this works way better than me, but I never actually did any Amiga audio programming back in the day. I never even got around to it, but I just thought I'd have a quick go just to see how hard it is. And it turns out it's not incredibly hard once you know what you're doing, and it's really easy for the CPU to do it. So very cool. That's how the Amiga, that's how you get sound out of it.